Year-old jewelry car.
Going on? It's been a while since I've been on here. Sorry if I'm clicking the audio. But yeah. Hopefully that didn't just dox whatever the stream key is. But it's been a while since I've been on here. Sorry if I'm clicking the audio. But yeah. We're just gonna call that good enough. So, still think I'm equipping the mic here. Test. Hopefully that's alright. We'll hear afterwards. So, looking at the channel here, it has been a minute. It's the last one. It's over a year ago. March 5th. Oh my god. Off by one day. What were we doing a year ago? We were working on Request. Using the same terminal setup. Hasn't really changed too much. This was a year ago. Wow. So yeah. Since this, it's been a long time. That's crazy that was not even a year ago. Yeah, since then, started a job, I've moved. Been working here for about 3 months. And yeah, I've really taken a break since last March from not only this like stream thing, but some just kind of like outside of work, outside of school programming in general. I mean, looking at the GitHub, not even logged in, but looking at the GitHub here, 2026, I really haven't done much. And then yeah, coming in 2025. Early year was different where I was doing a lot. Internship, didn't do anything. Some contributions in September, that's a web dev club. I did web dev club one more semester working on SAP Pin. It's like a random ass belly clone. Contributing on Christmas is crazy. What am I doing on Christmas on GitHub? But yeah. So I'm looking to get back into kind of outside of, I guess now it's outside of work programming. And what I'm really trying to do, I guess, the steps I'm trying to get into, I'm trying to get back into more system stuff. I think I have gotten a bit washed when it comes to like systems programming. So we're going to be doing some reading. I'm looking at trying to start contributing to Asahi Linux. It's like one project that could use maintainers that I actually enjoy and that I think is cool. And yeah, I'll probably grab a Bev first. We're going to be reading about the M1 GPU. I'm just going to poke around here, poke around on GitHub perhaps, and just see what's going on. So yeah, I'll be back in a second. So yeah, if you haven't already noticed, I have not gotten any more entertaining since the last time I was doing this. I think I just kind of realized. You realize at some point that you're just not entertaining, and even if you were entertaining, and you're reading like about M1 GPUs that nobody really cares. So I think that it's fun to just like do the stream thing because like it just changes up the flow, and I enjoy like going and looking back at them. Being like, yo, what was I doing on March 5th, 2025? I still can't believe this is only a year ago because it's been a while since I felt like I lived in a place like this. I don't even remember that tape on the wall there. Stood variant. Yeah, I was pretty like disciplined in keeping up with this stuff recently. But also since then, what's happened on the reading list? Shut up. What's happened on the reading list? I've read a lot since then. I think that was probably around here. Finished up some coursework. Damn, I cannot believe this is a year ago. Crazy. I feel like I've changed so much since this time. Sipping on the Coke Zero, no caffeine. It's too late for some caffeine. But yeah, you can kind of tell from this that I've kind of been moving away from reading about programming and just kind of reading about... I've been reading more fiction. I mean, this is like some of the first fiction in here. Goodbye Eri, Company, Metamorphosis, Death Note, Crying of Law 49, Look Back, and the Peanut Colony. Yeah, and this is a bit outdated. I guess these are still in progress, but I'm almost done with The Prince. Oh yeah, this is definitely outdated because I've read a lot of like politics in 2026 already. I'll update this eventually, but not already. Yeah, let's get to the actual point here and start reading this. M1 GPU. It's a GPU. You probably know what a GPU is. They have the same components. So I might even do we come into here into Requent. Let's clear out of here. A sessionizers and keep in mind that as well. This might even have my reading list updated. I think I was working on it a second ago. Book list. This is old. This is very old. This isn't even 2026. Let's get diff, see that. Oh yeah, let's get reset dash hard that, get pull. Let's clear that. Let's go into here. Now I think it's called reading list. Yeah, and we can actually, now that we're here. What have I read? I read Communist Manifesto by sorry, this is like the biggest side thing. That's not how you spell that. It's gonna be Freed Rich, like that. I also read this dissertation on colonialism. Or what is it? Not dissertation. It's like dialogue. What is it? I forget what the first word is. Discourse on colonialism. Colonialism. That's by Aimé Césaire. How do you say this guy's name? We'll capture the... Oh my god. Sorry, I got a new keyboard at work and I've been learning the new keyboards for that, and I'm just ruining the keyboards on my home computer now. How do you pronounce this? That's very annoying. One sec. I'm crying. Pretty eyes. I'm an idiot, one sec. Dude. Alright, we're using Bing on some random Alright. So back to what we were trying to do. How do you pronounce this dude's name, bro? Oh my god. Aimé Césaire. So this is the craziest rabbit hole of time. Hold on.
You are looking at Julian's.
Does it take a minute?
How do you pronounce the name of this poem? It is said as Aimé Césaire.
Aimé Césaire. Alright, Aimé Césaire. Alright, what else did I read? I'm also not reading. This is more backlog. This is more backlog because I'm prioritizing the Brothers K. Karamazov. How do they say it? Karamazov 11. So I'm gonna finish The Prince tomorrow. I'm just gonna go ahead and put it here. The Prince. Yeah. That's his full name. This is actually a pretty good read. I think it's also curious how like reading this and also studying like just politics in general, but also like the USSR and like even how like even Stalinism in a sense is kind of you can see the difference in the success of like Stalin and Trotsky based on The Prince, perhaps. It's kind of curious. Is that it? I'm trying to look at my bookshelf and see what else. I also read State Revolution. I think that's it. Alright, but that's not the point here. The point of opening this was to make a new note. This is going to be the M1 GPU. .md. Close this. M1 GPU. Paste here. That's a good title. Yeah, but the way I'm doing my dollar sign is a bit messed up though. We'll add an Asahi thing there. Alright, so what's the GPU? The same main components, they have shader cores, which process verticals. Holy, not reading correctly, they process triangles. Pixels by running user-defined programs. Got shader cores. What do these do? They process triangles and pixels. So we're not playing Counter-Strike right now. Process triangles, which are vertex data, and pixels, which are fragment data, by running user-defined programs. Let's whip up a chat. Let's whip up a chat and try to explain some of this. So they process shader cores. So let's say that we're reading this. So first question is explain shader cores. Holy ear itch, bro. Explain shader cores. So shader cores are tiny workers in the GPU. Each core can do calculations for graphics, mostly for rendering images on the screen. Modern GPUs have many shader cores working in parallel. So first are shader cores, 1, 2, 1 with hardware cores. Each core can do calculations for graphics, much as for rendering images on the screen. Modern GPUs have many shader cores working in parallel. So vertex versus fragment. Vertex is information about points in 3D space. Fragment is pixel. So for something like a window manager, or basically anything besides like 3D gaming or like graphics, it's all fragment. Alright, so this is some good notes here. Vertex is information about points in 3D space, positions, colors, normals, texture curves. So perhaps the third dimension is not necessarily like a z-axis, it's like color or something. Unsure. Fragment data, information for each pixel that we're putting on the screen. Fills in the shape defined by vertices. That kind of makes sense. Shaders come in two flavors. Vertex shader processes vertex data, transforming shades in fragment / pixel shader calculates. Alright, so what do we have here? Shader cores. So let's go. Let's do something like this. Notable GPU components. Go shader cores here. So is that something happening here? Shader cores. Shader cores process triangles. Vertex data and pixels fragment data. We'll do a site here. We'll just do like this for the whole time. How do you cite stuff? Where would I have cited something? Here probably. No. Here. Yeah, it's like that. So. Oh my god, I'm trying to do one. Alright. So let's go ahead and like develop this. Why is it not open in the directories on my redirect? Are you kidding or not? Always self-support. That's why we have a delay, buddy. So I was trying to deploy this. It's like npx. Is there index develop here? There is. There always is. Alright, beautiful. Oh, we are moving so slow right now. How long have you been doing this? 22 minutes? Bro. Alright, we're in the shell. It's gonna be an npx quartz build -- serve. It's been a while. Looks accurate. It's gonna be a local host 8080. Sounds good. So, noise is there's a space there at the top. Shader cores. Alright. So now we're looking a bit better. Shader cores process triangles. That's the style I've been using here. Triangles, vertex data, and pixels of fragment data. So we can do something here. We say vertex data is information about pixels in 3D space. Like positions, codes, normals, and texture coordinates. Defines the shape of objects. Then fragment data. It's information for each pixel that will appear on the screen. Each pixel on the screen, I guess. It's what fills in the shapes defined by vertices. So that just kind of sounds like words to me, Carly. So that's the two types. So then we learned that shader cores are not one-to-one with hardware cores. Hardware cores are either physical execution units. Shader cores are sometimes called ALUs. But that's even more misleading because they're programs that run on the hardware cores, they're not hardware. Right, so shader cores were called ALUs. with ALUs in a hardware sense. When they said ALU, they were talking about a hardware. Oh, it is a hardware circuit. This is in the old. In GPU literature, they said shader ALU, but they didn't mean a fully independent CPU-like core. They meant the part of the GPU hardware that executes shader instructions. I mean, yeah, that's not accurate. So okay. So it does have a basis in hardware. Actually, this modern GPUs work differently from CPUs. A single hardware core can run many shader programs in parallel using simped single instruction and multiple threads. Single instruction, multiple threads. Curious. So the number of shader cores in the marketing spec is usually more than the number of parallel threads the GPU can handle. Let's see. So we have a curiously horrible analogy. Hardware core is a chef, shader core is the dishes being cooked. Okay, I'm not reading. M1 GPU has up to 128 shader cores. I would expect more. M1 GPU has up to 128 shader cores, but those aren't 128 physical cores. They're units within 8 compute clusters that can handle. Okay. I've noticed something recently where LLMs will just like answer your question and then at the end just ask you another question. I don't know if they're trying to hedge like having too long of responses while also like chaining you into taking as many tokens, but I don't know, I found it kind of annoying. Explain why GPU split vertex versus fragment work across different cores too. It's actually clever. Alright, we're gonna have to lock it. If you want, I can explain why GPU split vertex versus fragment work across different cores too. Yeah, we're actually gonna mute this. We're gonna mute this and we're gonna lock in. Alright. And why GPU split vertex versus fragment work across different cores too. It's actually clever. So we'll come back to this, but yeah, we do just want to like make it through this eventually, but I do want to like learn as much as possible. Alright, so for something like a window manager, or basically anything besides like 3D gaming or graphics cell fragment. Yeah, so I was curious, like 3D, like nothing on the screen right now is 3D. So for most 2D stuff, like window managers, UI rendering, or video playback, fragment shaders dominate. Because you're mostly just coloring pixels on the screen. Vertex shaders still exist, but they're simpler. Even a full screen window or button is just a few vertices forming rectangles. So the vertex work is tiny compared to the, so on this. But what about this is 3D? Are you serious? Oh my god. Oh, okay. Just an ad. Even a full screen window or button is technically 3D data because GPUs work in 3D space by default. Every rectangle quad is made up of vertices in 3 coordinates, even if z is constant. So is that how window meant? So, we might have 4 vertices for the corners, forming 2 triangles. GPU still treats them as 3D geometry. As any transformations in identity, and then rasterizes to fragments. So is that third dimension like the Z in a CSS sense? It's like layers of opacity or something. I feel like it's not. It is, really. I was expecting that to not be the case. The Z in GPU returns the depth in 3D space. It does map to layer. So if I have a full screen window over a background, is a shader core rendering the background despite it having like I didn't realize that the logic that programmed that was like at the GPU level. I would have thought that was like CPU level. Or yeah, I guess I was curious. Usually no, not fully. It depends on how the GPU and the Windows system handle things. So I know I'm kind of like funneling into the Windows system. But that's just like the method I'm using to think of this right now. Naively no optimization. The GPU could run fragment shaders for every pixel of the background, even if it would be completely hidden by the full screen intro. That wastes cycles and energy. The optimized way that most modern GPUs and Windows systems do is early Z culling and a depth test. The GPU checks the depth Z of fragments before running the full fragment shader. Fragment is completely covered by something in front, like your full screen window. Skips the heavy pixel math, only fragments that will appear on the screen. Shader cores mostly only background fragments under a full screen opaque window will never hit them. Curious. Really? That's kind of. Wait, I'm actually curious. I'm impressed that I noticed something about that one in particular. Tile-based rendering. So traditional PC GPUs are immediate mode that write pixels straight to the frame buffer as they compute them. So the frame buffer is the frame buffer memory mapped pixel data for the screen. So let's see what the frame buffer is. I know we're kind of bouncing, going on a side thing here, but so the frame buffer is a chunk of memory that holds the pixel data for the display. RGBA, essentially. GPU renders your scene into the frame buffer. How many frame buffers does it maintain at once? So once the GPU finishes, the display hardware reads the frame buffer and outputs the pixels to the monitor. Makes sense. On systems like the M1, the frame buffer may be tiled in memory, not just a flat 2D array. Efficiency tiled. Maybe tiled in memory for efficiency. Tiles mapped to how the GPU is tile based. Ah, okay. So we need to learn more about tile based rendering to understand that. That helps the GPU. Alright, so yeah, we're going another side thing here. Single versus double versus triple single. Can cause tearing because you're writing to it while it's being read. Double. Write to the back buffer while displaying the front buffer. And then I guess you just add more of these and has more lanes. When done, the buffer swap or copy reduces tearing, triple buffering. That's another back buffer, so the GPU never waits for the display to finish swapping it. It's like if the swap is slower than the. That would be useful if the swap latency was slower than something. So we'll skip figuring that out for now. Modern GPUs. So the M1, like most modern tile-based GPUs, uses double or triple by default. The exact number can depend on whether it's the main macOS. Oh, that's kind of cool. So what is a metal at? So it doesn't matter for now. The system may allocate extra buffers for UI compositing, video, or off-screen render targets. Even if the GPU only draws one logical frame buffer internally, it often keeps tile buffers and depth stencil buffers per tile in fast function memory. These are temporary and not the main frame buffer in RAM, but they often rendering more efficient. Sure. So this will be like the last one we do here. So renders full screen windows efficiently by tile-based deferred rendering. So let's go back up and read that. Let's go back up and read that. Yeah, we went on a few tangents here. It's the first instance of. Bro, where's my control key? Dude, I gotta get my other keyboard. This is getting ridiculous. So this I don't know how to read anymore. The screen is divided into small tiles, 1616. Each tile has a tiny on-chip buffer for color, depth, and stencil values. The GPU does all the fragment shading for the tile in fast on-chip memory before writing into the main frame buffer RAM. So, what on-chip memory does the M1 have? How many levels? Why full screen windows are cheap? If your window is opaque and covers the whole tile. The whole tile, okay, that makes sense. Skips shading any background fragments for that tile entirely. If then only the final visible color for each pixel, it then writes only the final visible color for each pixel. Yeah, so it doesn't have to compute the opacity of the layers. Or even mixing the layers on top of each other like I have here. If this is not on like a chunk border. Efficiency games, so you have fewer frame buffer writes. Why is it fewer frame buffer writes? It's fewer frame buffer writes because there'll be some parts of the screen that don't change. And if a tile doesn't change, then you don't write the whole tile. Whereas before, without tiling, if any part of the screen changed, you have to rewrite everything. Is it fewer frame buffer writes because a tile unchained on a frame needs no write, whereas if you had no tiles and even changed 1 out of like 1,000,000 pixels, this is something where I could see the dictation being useful. Because like by the time I type this, I'm saying it and I'm saying it like half the speed. Whereas if we just talk about this, it's a bit of a curious way to like learn stuff, maybe. I don't know. So M1 memory, so sure. Shader register files. Each shader core has registers for temporary per thread data. Yeah, so we're still talking about GPU. So yeah, the whole, yeah, for some reason when I was thinking this on-chip memory, I was thinking of CPU before. I guess it's not entirely different. Tile buffer, sometimes called the render tile buffer, or the render cache. Stores color, depth, stencil. Color, depth, and stencil. So color is immediate. I don't know. Depth is like Z level. What is it called in CSS? I was going to say Z score, but that's like stats. Z level? Z index. Depth and stencil. So we're going to figure out what stencil is. What is stencil? I'm assuming depth is Z level. Z index. Alright. Small but fast SRAM to hold the tile. After shading, it's written to the main frame buffer memory in one burst. So, at a hardware level, what is allowing, or what is mapping the tile buffers to the main frame buffer? Is it mem mapped? Is it like a direct hardware copy? A dedicated wire? Alright, so back to this. What is stencil? Assuming depth is Z index. So depth is Z index. Z. Yeah, I'm really surprised that the third dimension is really just like layered on the screen. I thought that would be encoded somewhere else. That is curious. And then if it's like a game, so then like the 3D rendering of a game makes that's something we'll figure out later. Yeah, it's used for hiding pixels behind others. I can't believe that's kind of dope. Stencil buffer stores a small integer per pixel. It's a mask. It's often 8 bits. If it has mask, you can test against when drawing. So when I hear mask, I'm thinking of like add, multiply, subtract, burn, overlay, like those. I don't imagine it's that, because this is all... What is the default? Normal. I was gonna say default, but it's like, I guess it's kind of normal. So it just replaces it, or just, yeah, okay, that makes sense. Just a mask. So common uses for complex shapes. Draw into the stencil buffer to mark a shape. Excuse me. Later, only allow rendering outside the shape. Excuse me. Outlines and shadows. Really? I didn't realize it was that optimized. I thought you just drew pixels. I thought you just drew pixels. Bro. So outlines and shadows. Draw stencil values where an object is. Offset and draw only with a stencil. X. So the stencil is like an offset. So yeah, our notes are very behind, but we'll catch up to them and kind of know what's useful out of here to write and like look back at later after we're done. To give an example of this, the stencil would hold like the border radius. What function takes number in the stencil and outputs the effect of it to a tile buffer? What if this outline flips to another tile? Since, and then what else should I ask? So to continue, so it's like also on a screen, one tile touches 4, 8 with diagonals. Other tiles, these can't all be contiguous. Memory. So how do you synchronize them? Alright, so that's a few questions, but I'm actually impressed with the free ChatGPT answers. Unless this is just all false, so that'd be kind of annoying, but so what were we asking here? This is figuring out what a stencil was, so let's go through this. Mirrors and portals. Mark regions where reflections or special effects should occur. Nah, I didn't realize it was this. I didn't realize like the GPU architecture was computing these. I guess I didn't really stop to think what it would be. But... So in a window manager, depth handles layering or bordering in windows. Whenever I say it, it sounds horrible, but I'm still reading the actual words. Stencil could be used for non-rectangular window shapes, rounded corners, or special effects. What I can give you a kind of diagram. I don't really care for that. So yeah, because the leading questions, some of the questions that I asked were actually useful, but so maybe I don't hate it, but it's still just kind of corny. Like I just, like in principle, if I ask you a question, I'm not trying to just have you. I'm not trying to have a conversation with AI about a bot every time I'm talking to it. So we asked at hardware level, what is the mapping the tile buffers? Okay, what is mapping the tile buffers to the main buffer? Is it mem mapped? Direct hardware copy on a dedicated wire. So tile buffers to mainframe buffer the M1 way. The M1 process is roughly tile shading is on-chip SRAM. Each tile 1616 is fully shaded inside the GPU. Okay, so it's using the fast on-chip tile buffer. That's color depth stencil. Flush to mainframe buffer. Once the tile is completely done, the GPU writes the tile to sys memory. I see. This is usually a burst write over the memory controller. Okay, so it's not taking half your PCB. The memory controller handles the transfer efficiently, often using DMA. Beautiful. The mem mapped yes and no. It's in DRAM mapped for the SRAM. Yeah, so that makes sense. This, the on-chip SRAM internal to the GPU temporarily with shade. GPU's logic handles copying tile buffer to the frame buffer. I'm surprised that's not super latent. Because 16 by 16, you have a 4K screen. You're just using memory controller. Honestly, I might try the voice thing. Once we get through this, I'm going to ask about that. Hardware copy details. Yeah, it's not CPU style copy where you move X pixel one by one. The tile buffer is connected to the GPU's memory controller via high-speed bus. It is written in bursts. Reduces DRAM transactions. That's why it's power efficient. That is kind of curious there. Noting that it's power efficient. As opposed to any other efficiency. I'm not liking the analogy. I feel like understanding this is harder than just reading this. I'm not trying to think about a notebook and a filing cabinet and then map it back to this when I could just read this. Alright, so we're good on the diagram for now. So we wanted an example of the stencil with the, yeah, so we had a lot of questions there. It's like a border radius, and then about the memory stuff. Stencil example, border radius. The stencil is often used for masking effects like rounded corners. So that's not exactly the same as what I was trying to say. Write the stencil mask. For a rounded rectangle, you run a stencil pass. You shade the shape, but instead of writing color, you write an integer to the stencil buffer. Oh, so is that 16 by 16? Is the stencil buffer same size as the tile, 8-bit for each pixel in it? I thought it was saying it was an 8-bit number for the whole tile. That makes a lot more sense. I thought the stencil was just an 8-bit. I was like, what are we doing in the stencil that this is useful, right? Yeah, okay, it's 8 bits for the whole tile. So that makes more sense. So that could be like an opacity, that could be a... So yeah, this is 1 inside and 0 outside. Okay, that makes more sense. Use the stencil to control shading. When you later draw the content background with a fill shadow, the fragment shader checks the stencil value. So here we're still talking about the vertex shader, right? Then you have the fragment. Or are we? That's probably not the right diction there. But regardless, use the stencil to control shading. When you draw the content, the fragment shader checks the stencil value. If stencil 1, draw, I'll skip. So this. Is this done using matrix alt? Is that why GPU stuff is useful for large AI stuff? Alright. So, how stencil affects the tile buffer. The GPU pipeline has a stencil test stage and hardware. Functionally, the stage look like if stencil test pass. So, I'm never seeing how this is a test. I think I'm seeing test pass after working on the type of stuff that I've been working on recently makes me seem like it's a test that's fast. Stencil test pass, current stencil value, ref value, right color. We'll skip. If the stencil test pass, this stencil test pass, stencil value and the reference value. So this is like applying the mask. Okay, that's why they're calling it a mask. And this function determines how these interact. Then inside the tile buffer, watch the DRAM. Tile buffer itself holds color, depth, and stencil arrays for the tile. What if the outline clips to another tile? Good point. Tiles are small, so sharp, the shapes often cause tile bounds. Each tile knows about its own pixels. Okay, so it's doing that calculation independently. So I'm so curious how that's synchronized, because like shape here. Maybe it's not. Stencil. So how long are we going here? 50 minutes? Making them solid early. Stencil values are written per tile, so it doesn't matter. Shape is just split, and it looks seamless because tiles are adjacent. So when I was thinking of like what is driving this, I guess it doesn't matter because this is at the very last level where the only thing we just bring them together by the nature of writing them. They're like writing them to the thing they're mapped to properly in the frame buffer. Sure. No need to synchronize across tiles for stencil. The shape is just split across tiles. The result looks seamless because tiles are adjacent. Tiles don't need to be contiguous in memory, so yeah. So yeah, that makes sense. Tile adjacency in memory. You're right. Tiles on the screen are not contiguous in DRAM. Yeah. So yeah, this question was kind of nullified after we learned that the memory controller is writing them from on-chip SRAM. I need to revisit SRAM versus DRAM. From on-chip SRAM into DRAM. Right? Linearly or in a swizzle pattern. Sync is per tile, not pixel. Tile n knows nothing about n+1. The final frame buffer assembles all tiles in the correct screen. Seamless visuals happen because, with only the knowledge of its pixels, utilize it in the frame buffer. Yeah. No analogy, please. So yeah, that made more sense. I thought stencil was 1 8-bit number per tile. I was like, that's useless. All right. Is this done using matrix mult? So this is that. This is that. So this would be like, yeah, so you can see this is like a matrix where you have 16 by 16 with the stencil, and 16 by 16 with the color, and if it's 0 pixel, it's like getting nullified color. So you don't write it. So let's see, the stencil itself. The stencil check itself is not a matrix multiply, it's just seeing if it's a 1 or not in that case. But certainly there's cases where you're using more 8 bits to compute something complicated. It's like mass, yeah, okay, that makes sense. So GPUs are good at linear algebra and AI. They excel at matrix and vector operations because of SIMD, SIMT. So yeah, single instruction, multiple thread. I was curious, like, what is that? SIMD. SIMT. Oh, that word. I don't know. Shader cores run this. Excuse me. Shader cores run the same operation on many pixels in parallel. True. This maps perfectly to matrix multiplications, which are the same operation applied to many numbers at once. High throughput. Thousands of ALUs. Thousands of ALUs. But the M1 only has 128. Where were we? Modern GPUs have thousands of arithmetical units optimized for multiply adds. Some products. It's exactly what deep learning does in dense layers convolutions. Memory coalescing. GPUs like the M1 can read-write contiguous blocks of memory efficiently, similar to how tile buffers handle the 16. Same. Alright. So key takeaway. Stencil uses the same hardware as Matrix Ops, so the Matrix view is jumping forward a bit and a bit inaccurate because it is really just a mask in the case of the game. So yeah, they said thousands of ALUs with the M1 at 128 that they said. Shader core is not a single ALU, it's a vector of ALUs. Curious. Apple calls them cores, but inside each core there are many execution lanes. The 128 shader cores might have hundreds of. Oh, real? Okay, that's crazy. Hundreds or thousands of ALU lanes. That's a lot. 128 cores with thousands of lanes. So where's my what schedules what tiles go to which lanes? Are there concerns? So are tiles always mapped to the same lanes? Probably not. With the same cores? Are there like memory concerns? Is it like a CPU in this way? It's the first question. And note that we're still on the first bullet point of this. And we haven't even looked at fragment data. We're still doing vertex data, basically. But I do think this is the way to do stuff. Like, if I'm gonna read this with the intention to like work on it, and not even just work on it, but actually improve it, and like make contributions that other people can make, like, this is what you gotta do at some point. Single instruction, multiple threads. I'm still not seeing what exactly, because I mean, I guess it's implying that you're using the same date. Like, I mean, you're running the same instruction across multiple threads, but like that being related in any way kind of implies using the same data. Each shader core schedules a tiny thread zone. Even if a core has 4 ALUs, it can time slice. What's time slice? So 128 shader cores can saturate the GPU with thousands of concurrent operations. Sure. Time-based advantage. And so I guess the appeal is the power stuff they're saying. ALUs are never idle. Scheduling in parallelism logic. So yeah, this isn't even really about, I don't think the Asahi Linux cares about this, but I think it is just useful to know. Who schedules, so what is the time check? 12:30. There's a hardware schedule. Oh, really? It's in the. So I thought the CPU scheduled the GPU, but this is saying there's scheduler logic in the GPU. Take all the tiles that need shading and assign them to shader cores. Entirely in hardware with no CPU intervention is based. not permanently bound to a core or an AOU lane within the core. A given tile may get to any shader core that's free. This is called dynamic load balancing, so that can make sense with this. The scroll was so disorienting for some reason. Okay. Are tiles always mapped to the same lanes? So you just said that? No. It's just exactly what you just said, okay. Memory collision synchronization tiles are independent. Each tile has its own on-chip tile buffer. That makes sense. No memory collisions while shading tiles on chip. So I'm curious how much depth. It's like 8-bit depth implying 256 layers is kind of ridiculous unless it's like you're using the third dimension for something else in like more complex 3D. No memory collisions while shading tiles on chip because each tile's data is private. Sure. It's not wired or anything besides the memory controller. Only after shading is the tile flushed to main memory. Sure. Multiple cores. So also or was it 120? No, it's like thousands. 128 cores, but so each shader can't physically execute threads. Yeah, the dudes that make this. So I'm definitely getting tired now. I'm a bit fatigued. It's 12:30. Gonna wake up 9. Yeah, we'll lock in a bit more. Alright. So how are there no bottlenecks in the memory controller? How concurrent is it? Now we're at the heart of what? Ah! I like these little uplifting intros. You're right. Naively writing thousands of tiles to DRAM could be a huge bottleneck. But Apple's M1 solved this cleverly. So the M1 is an integrated chip. Most fragments never touch DRAM. The final color. Why do most fragments never touch DRAM? So I think I'm not properly mapping fragments and cores. So fragment is information for each pixel on the screen. Fragment. So this must be a little bit of a different context on fragment. Hidden pixels inside tiles are never written. That makes sense. There's more. Okay. First writes each tile flushes to DRAM. First. Pixel by pixel. DRAM is optimized for sequential. This is fast. Sense. Short competency and multiple standing actions. M1 likely uses multiple banks of DRAM, so tiles from different regions can be written in parallel. So this I'm not going to go too far in. How concurrent is it? You have many shader cores producing tiles in parallel. GPU memory controller buffers the tiles and issues multiple DRAM writes at once. Often a write queue. Stop the analogies, please. How tile-based memory reduces bandwidth. 4K screen has 8 million pixels. Tile it. You got 16,000 tiles. Fully integrated system on chip. Oh, even the memory controller is on that. So it's not on the PCIe bus. That's a good point. On the M1, GPU shares the same physical memory with the CPU and neural engine. I don't know what a neural engine is. The M1 has 16 gigabytes of dedicated. Really? Oh, it's unified. Really? I've never heard of. Hey, this is kind of crazy. I'm not knowing any of this. The integration helps the GPU because shared memory equals fast tile flushes. GPU can write tiles directly to main memory without going over a slow bus. No copying between VRAM and SysRAM is needed. Faster scheduling. GPU can generate draw commands and shaders faster because it's on the same chip. Power efficiency. That makes sense. I'm gonna drive a long bus. This is incredible, Loki. GPU sees memory as just RAM. Sees memory as just RAM and not a frame buffer. Oh, because that's. I said it wasn't mem mapped. Stop with the like what? Like why? Why do we need this, bro? See how they share the memory? Dude, I'm so tired. Alright, GPU sees memory as RAM, not VRAM. GPU sees memory as RAM, not VRAM. You has its own dedicated RAM, VRAM. If you can't access it directly, you gotta copy it. It writes directly to system DRAM. So I need to see explain DRAM versus SRAM versus VRAM. So it is memory mapped. Wait, hold up. On the M1, there's no separate VRAM. The GPU does not need special memory mapping for the frame buffer because it's just reading directly from it. I see. Wait, so the GPU writes directly? Damn, okay. But the GPU doesn't have a separate VRAM space, it's just RAM. Yeah, okay, so I'm just being an idiot. So tile buffers on chip SRAM. Only after a tile finish, you can flush the VRAM. Okay. Appreciate you. So Neural Engine is Apple's dedicated AI accelerator. Multiply accumulate. So when that was multiply add, this is multiply accumulate. So curious. Now the whole like multiply accumulate stuff is kind of crazy. Like even on the Punt Engine project, like just the basis of everything. Shares the same unified memory. Poetry parallel. The DRAM is dynamic RAM. The 4 yawns per minute is a sign here. Dude, we're on the first bullet point, bro. Let me go up. Alright, the main system memory RAM in most computers, the M1's unified memory. It's volatile, slower but dense. Needs refresh cycles. Data stores with tiny capacity. One's a frame buffer, texture, CPU data, GPU data, neural engine data. Just a bunch of random trash, basically. I mean, not trash, but transient stuff. SRAM is static. Very fast. So these are the smaller ones that are more expensive. It's fastest. Image capacity. Caches, tile buffers, shader registers. VRAM is video. Yeah, I didn't know what VRAM was. Video RAM. Memory dedicated to the GPU. There's no separate one because it just uses the DRAM. Okay. So, no, I think we're ready to go back up and talk about fragment data. Holy shite. I like how it's on the left too, just because I have this thing set up. So I think we're finally ready to talk about the next one. Yeah, so that was 1 out of, oh my god. Alright, so let's just move on. So you got rasterization units. So these are like 4 different rasterization units, texture samplers, render output units. This sounds like load something from memory and do something with it. Yeah, thank you. Very useful description there. Other bits which work together with the shaders to turn the triangles from the app. Yeah, so I don't understand the triangles. Like they're saying have a square, triangle. Then that seems like it's cutting. That's like maximizing the amount of split tiles. So yeah, let's try this now. Can you explain the tiles thing? Or sorry, the triangles thing? Because imagine you have a rectangle and you cut it a triangle like down the hypotenuse. It seems like that creates the most amount of splits among the tiles within it. Whereas if you just cut it into like a smaller square, then you could cut it directly on tile boundaries and have it better. Though maybe I recall what you were saying that it doesn't really matter that it's in split across tile boundaries because the tiles are independent. I'm curious, like what functions. I guess yeah. Just explain like what the triangles do. So why do they draw triangles instead of rectangles? Graphics 101, but deep. Holy cornball! Right. Triangles are the simplest polygon in 2D space. Always planar space. Holy based graph theory. Uh, hmm. Triangles planar. What is planar 3D?
Hi, glad to meet you. I think we're gonna do.
Oh my god, I
it's great to
hate
meet
that.
you.
I
Hey,
hate
how's
that.
it going? I'm looking forward to working together.
Hey, I'm ready to hit.
Hello, it's lovely
Alright,
to meet
let me
you.
log
If there's
in. I'm
anything
curious
you
to
need,
play with
please
this.
don't hesitate to let me know. I'm here to help.
I'm here to help. Shut up. What account is my chat? Давай, это так. Блять. Ладно, skip. Сука, ты.
Of course, I'd be happy to. Just let me know which part of the song you'd like me to
Yo,
explain.
shut up. What the hell? Oh my god, stop talking, please. Alright, so. Dang it. So I made an account, but it deleted the previous thing we were talking about, which is kind of annoying.
Hello.
Hey,
Hey, how's it going? I'm looking forward.
hey, I'm ready to.
Hey, what's up?
Hey there.
Hi there. Nice to meet you.
Hey there.
Hey, what's up?
Hey there.
Hi there.
Hey, it's great to meet you. How's your day going?
Hey, which one of these is
Hi,
like the least
glad to meet you.
off-putting?
I think we're gonna do great work.
Can't be
there.
British.
I just want to share how thrilled I am to work with you, and I
Hello.
Two
It's lovely
oncoming.
to meet you.
Hey,
You
I'm ready to
oncoming.
hit the ground running. So if there's anything you'd like me to.
Hey, how's it going? I'm looking forward to working together. Let's.
Hey, what's up?
Spruce.
Feel free to ask me about anything.
Hey there. I've got a really great feeling about us teaming up. How can I?
Hi there. Nice to meet you. I'm excited to help you get things done. Let's.
Hey there.
Hey, what's up?
I don't have a
Hey,
problem
how's it
with
Hey, what's
Spruce,
up?
Soul,
Hi
or
there.
Juniper.
Hey, it's great to meet you.
Hi. Hey, what's up?
Start
Hey
with
there. I've
Juniper.
got a really great feeling about us teaming up.
Is this where is this talking right now?
Ah, good question. Yeah, it does have a bit of a blog-like vibe, but it's also
Wait.
kind of a living technical journal, so it's definitely aimed
Wait.
at engineers and developers. I mean, some posts are pretty deep dives into kernel development and reverse engineering.
Hey
Wait,
there.
what happened to
I've got a
talking to
really
it?
great.
Hi there.
Hey there. I've got.
Hello? Hello, test, test.
Hey, yep, I'm here. Just let me know what you'd like to talk
Alright, yeah,
about.
I'm trying to
or if
figure
you have
out I'm trying to figure out why. So in an earlier chat that we lost, it was said that whenever you draw a rectangle, it's divided into triangles, and this is because the triangle is the smallest shape in 2D that's planar in 3D. What makes it planar in 3D? Because if I'm thinking of planar from like a graph theory sense, like, oh, you can draw it without having overlapping lines. Like, if a triangle, any 2D shape has that property in 3D, because you just pick the lines up and lift them off of each other and use the z-index to just kind of have infinitely many levels. So, like, what does that mean? What? Dog, lost connection. No, dude. Hello? Bro, this is rage, man. Can it at least say what I had? Hello?
Hi again. I'm still here. If there's something you'd like to discuss or ask about, just let me know.
Okay.
No problem. If anything comes up, whether it's about the Asahi Linux blog.
Yeah, okay. So when you're having rectangles on the screen, it was said that the reason that you divide them into triangles is because a triangle is the smallest shape in 2D that is planar in 3D. What does that mean to be planar in 3D? Because if you imagine any 2D graph, even if it's non-planar, you could make it planar in a third dimension just by, for every like intersecting line that you have. Why does it do this? What? Lost connection. Dude. Yeah, let's just use this. So, since it is the case that a what's the word? So it was said that a graphics processor divides rectangles into triangles because triangles are the smallest shape in 2D that is planar in 3D. How does this work from like a graph theory sense where any even non-planar 2D graph could be planar in a third dimension just by increasing the z-index of a line intersecting another based on like what, just like for each line in the graph. So like what is an example of a 2D shape that wouldn't be planar in 3D? What is meant by that? Mixing ideas that sound similar. Geometric planarity and graph theoretic planarity. In math, planar is not equal to can be separated by lifting things in 3D. So maybe that's more specific thing I was thinking of. When graphics pipelines say triangles are planar, they mean something very specific. They mean that a triangle is defined by 3 points. Or I guess it's really that in 3D space, any 3 points always lie in a single plane. Well, yes. And a square. So what is a square that doesn't lie on a single plane? It is one with 4 orthogonal points. If it's 3D. What is an example of a square that's not planar in 3D space? Wait, what? Last. So a square is planar in 3D space, but this thing a square isn't planar in 4D space. A 4-point shape. Oh, okay, a 4-point shape, a quad that looks like a square and connect. These points don't lie on the same plane. Plane is 2. This is because you have 1, 2, 3. So it's non-planar because there's 3 independent vectors, linearly independent vectors. It's not because there are 3 linearly independent vectors, it's because the vectors you get from the points span 3D instead of a plane. Take ABCD, you have AB, AC, AD. So if all 4 points on the line, the vectors live in a 2D subspace. 1 point is off the plane, the vectors span full 3D. A quadrilateral is planar if it only have 3 vectors are linear. Oh, if they're dependent. Oh, okay. Oh, so it's saying that 2 of them could be, yeah, that makes sense. Wait. How is saying that if a quad has 3 independent vectors, it's non-planar, and saying that if a quad has linearly dependent vectors, it is planar? How are those two different? Bro, what? You just said this wasn't right. Huh? Am I tweaking? Nah, this is pissing me off. Wait, am I dumb? You just said this was wrong. Then said that the equivalence of my wrong statement was correct. Unless I'm missing something. I'm assuming that all three vectors are taken from the same starting point. Assuming that all three are taken from the same starting point. I'm assuming that all three vectors are taken from the same starting point. How would they not be taken from the same starting point? Where would you start? Just drawing random lines in them. How would they not be? Yeah, I think this is getting a bit out of the scope of what I'm trying to get to before I go to sleep, Loki. Let's go back to, so that's the triangles thing. So back to the triangles with graphics processing. It seems to me like a square would be better because you could line it better on the tile boundaries of the tile renderers for the M1. Does it not matter that having a triangle go across a rectangle along the hypotenuse or something is making the maximum amount of tile intersections possible? For one line, I guess. You're thinking the screen is divided into tiles, a square nicely aligns the tile boundaries, a triangle, especially like a perfectly continual one, might slice across many tiles. Triangle crossing tile. Thanks for the image, dog. It would be a problem if GPUs processed primitives in the way I'm imagining. Tile ones. They're tile-based deferred renderers. They transform tiles to screen space. Sorry, they transform triangles. Arrow screen space. Bounding box for each triangle. Assign the triangle to all tiles that overlap the box. Inside each tile, rasterize only the driven mostly by the bounding box. Diagonal. That makes sense there because it's just a function of the ALU, which is also called the shader core. It's a function of the shader core to that tile. Doesn't matter. Square versus two triangles. Square is not actually a primitive in modern GPUs. Two triangles. Diagonal cost, extra tile cost, not really, because the tiles are going to be rendered either way. And the tiles aren't going to be, well, it depends on like if it's changing or not, but it doesn't matter. The triangle was changing there, or the square was changing there, it'd still be changing. But actually, this actually lets there be less change. But in that, yeah, okay. Rasterization is pixel precise. So we still don't know what rasterization is. It's the next part. Inside each tile, the GPU checks coverage per pixel. Unused pixels are rejected cheaply. Overheads are prioritized. This tile setup cost is small compared to shading memory. So all right. So what's the time here? It's been an hour 30. Holy raspy, like vocal fry. Alright, so we didn't really make a lot of progress on this, I'm not gonna lie. He made one bullet point, but I did learn a lot. Do I want to get into rasterization units, texture samplers, render output units, and other bits which work together with the shaders to turn the triangles on the app? So, triangles into pixels. Okay, rasterization. Let's do this and then go to bed. So, in the article on this bullet, what are each of these parts? Shader core. Yeah, this is gonna be like a bit unsustainable staying up 1 a.m. I have to figure that out. Ideally, this would be like a morning thing that I do on mornings that I don't go to the gym or something. Yeah. Big picture first thing of GPU. So great questions. Bullet basically submerging the entire graphics pipeline after vertex shading. That's useful, yeah. Wait, after vertex shading, I thought we just wrote it to the frame buffer. Ah! Big picture first. Think of GPU as two kinds of units. Programmable. Shader cores are what you write. Ah! So this is like CUDA. Shaders. So people say when they're writing shaders. Fixed function is everything else. So this is like, the shader cores uses, so when you write shader cores, dude, I'm so tired I can't even like type. Like, I saw the words and I was reading it back and like lagging. When you write shader cores, that's CUDA. Our CUDA programs functions of matrices of color, depth, and stencil. I was about to say shader. No, shut up, idiot. Shader cores are the GPU's programmable ALUs. NVIDIA hardware. CUDA is a programming model. Shader cores are hardware goes. Right, kernels. Yeah, so the matrix is like unproductive thinking, and it's just me trying to be like annoying. One clean mental model. CUDA, run math on big arrays. Shaders, compute values for pixels of vertices as part of render. They're both instances of data parallel programming. Just with different semantics. Let's back to this. So, big picture first. GPU is two kinds of units, programmable and fixed function. Vertices, vertex, so these are the vertices of triangles, vertex shader. There's like all this junk. Rasterizer does something. Okay. That's what it goes from restaurant. I can't even breathe, bro. Rasterizer, fragment shader, ROP? What was a ROP? Render output. Part. Sure. What is a ROP? Render output units. Where's the P? Render output units P. What are we doing, dude? ROP stands for render output unit. I'm crying. Good old invert. It's an unfortunate inversion there. -1 to an odd power has been applied. Well, that's why we have 0 viewers. Alright, rasterization units map triangles to pixels. Units. This not decide, because they don't decide it, they figure out which triangle covers. They do what? Take a triangle of vertices, screen space, a bounding box, walk over the pixels that we in the box, side pixels are in the triangle. Generate fragments. Outputting fragment words y related vowels. Why is this not working? Others using oh sure, I don't know any of the optimization. Appreciate you. That's a flashbang. I'm not going to sleep for another 5 hours. That's so even worse. The shader course. Let's just skip here and kind of get the notes down. Low key, I'm kind of good at that. Alright, shader course. Wait, we just did shader course. We just did shader course. What about texture samplers? Texture samplers fetch textures from memory. That was my intuition. Okay. And a filter. Bi/trilinear. It maps. I haven't done in a while. Addressing modes. RAM. Lamp. They have their own hardware as if they're hardware, they're regular. They're heavy. And special. Here it is. Render output units ROPs. I refuse to call them ROPs. Are the final step for Buffer. Okay. Depth test. A stencil test. Then transparency. Alpha conversion. Right final pixel data. Right final pixel. Vertex shader, input 3D vertices, output single space triangle and attributes. Rasterizer takes the triangle, finds covered pixels, generates the fragments, the fragment shader. For each fragment runs the code and asks texture units or data to help that. Texture units. So this is implying like not a synchronous but a combinational interaction. Props, depth mode. Additional waiver, why this split exists. Each one has specific needs in their hardware. Sense. Okay, so finally back to Asahi Linux. When Asahi talks about these blocks, they're reverse engineering how Apple's GPU implements them. And writing drivers that map the concepts to Apple hardware. Very nice. And the line, exactly how this works from GPU. Oh, that's a good link to the reorders the pipeline. So it is a pipeline. Oh my gosh. No, this is kind of cool. Like, you can actually get pretty deep into this. But let's not answer that yet. So I think I'm satisfied with this for now. Let's just see what this looks like on the site. We don't have anything else down here. So this is gonna be like Mac M1 GPU. Apple. Apple M1 GPU. This kind of that's like closest to my Apple M1 GPU. There's this. Beautiful. Alright. So I'm going to bed, Doug. It's 1:13. But let's just wrap it up real quick. Been on here for almost 2 hours. It's good to be back. It is good to be, I do think, talking through stuff and just kind of committing to sitting here and like being on a camera despite the privacy concerns is good for me. I think it does make it like funner to do work, and it also just kind of is fun to see how, like, in the past, how I did stuff, even like what I looked like just feels so much different at this point. Look at this kid with 6 views, just, you know. The hair used to be way like, hair there is interesting. Nah, I wish my hair still looked like this, Loki. Kind of like earlier now. Interesting. But yeah, I think it is. I'm curious, like, what drives the fact that I really enjoy streaming on March 5th. It's been exactly a year since my last one. It's kind of crazy. But no, it's good to be back. It'll be good soon to hopefully do some more programming things. But at first, I think what I'm going to be doing is a lot of research because I'm trying to contribute to more long-term, more complicated projects outside of work. I do think a lot of the type of open source stuff, even like this thing that I was doing here a year ago, this is really just better done by LLMs at this point. Like this thing that I was writing, if I was writing it now. Though it was super cool just like writing this. Just like sitting here and writing this. It's like even if I sat down now and tried to write this, I'm probably worse. Like this C++ template, I could not write that right now. So that's curious. I do think that's something that I would just chat at this point. Whereas the type of stuff that would be useful to a project like Asahi Linux requires this like research and domain knowledge that is just more useful to build, and it's like funner. And it's just better for my career, I think. So what I'm planning for the next few months, I would really enjoy like staying on this topic. Perhaps not just the GPU, but the Asahi Linux project in general. It's a good way to get better at systems programming and to work on software, hardware that tons of people use and software that I personally use. So, pretty cool. I know the project kind of needs in Python. Really? Okay, we gotta read some more of this later. But yeah, it's been a while. I'm going to bed.